in na sang exception majo thesis thesis compare skill la ma ang dan khai makati ya wa first 3 chapters
yeah
전 이제 sakdaga lobby
ya kati PhD PhD kan bhai me thesis reviewer ko khan mo hakimi ta ka kira dicekta ya kata haju okay ya masih kata result ke schema result ko dang de ya royal instructor ni kati mo taruh kati play pala satu dua maka review dan ada ya
yes we have 52 participants now, so let me share the PowerPoint. Yes. Is it visible? The PowerPoint I'm sharing now, is it visible?
Yes, sir.
Okay.
Yes, sir.
So I think we can continue from there. But before that, what I have to do is, make it a full screen. So, please mute yourself, everyone. So this is where we end our previous lecture, that we have discussed the physical meaning of gradient of a scalar function. So what we concluded was that gradient of a scalar function defines, please mute yourself. Gradient of a scalar function defines a direction in which we have a maximum change in the function. The direction of maximum change in the scalar function is defined by that gradient of phi, gradient of phi, the scalar function. Now let us look at what is called divergence. So as I said before, a vector quantity which depends on another independent variable is called a vector function. Now this is how we estimate, or how we take the divergence of a vector function. Like the one shown here, this is a vector quantity, and the x component a1 is depending on x, y, z, and similarly the y component a2 is also depending on x, y, z, and a3 is also depending on x, y, z. So if each of the components of this particular vector is depending on the space variables, then this vector is your vector function. The vector quantity which varies with space. It varies from one point in a particular space to another point in the same space, right? So divergence is when we have a vector operator, that is the del operator. We have talked about this del operator, right? Back in, I think, here in this particular slide, this is called a vector operator. It does not have any physical meaning. It simply means that this is a kind of vector operator. this del operator as it is, you cannot make any interpretation out of it, but it operates on any function which depends on x, y, and z. So it consists of partial derivatives of x, y, and z along with the vector unit vectors. Yeah, please mute your microphone. Mute your microphone. Everything is being recorded as well. Someone has not muted himself. Please mute. I have to mute those who doesn't know how to mute themselves. Who is this? Laldan, try. Please mute. I cannot mute you. I cannot change your status. Please mute. It disturbs the class. Okay. So this del operator is a vector operator, and A is another vector quantity. I think in your class 10, in your class 11 and 12, you already know that there, as I discussed, there is a dot product, and cross product, dot and cross product. Always remember that this dot and cross product are this dot and cross product is the operation between two vectors. Okay, this dot product or and cross product, they occur between two vectors. They occur between two vectors. That means what I'm trying to tell you once again is that probably most of you already know. Suppose I have a scalar quantity like A is a scalar, and suppose you have a B vector, B is a vector. You cannot write A dot B. Okay, this dot operation and the cross operation is between two vector quantities. Again, somebody is not muting himself or herself. Please.
Để tôi lại cả lọc thu cả hành tum mày xe cả hành tum đó chả bơi nhỉ.
So you see that one is a scalar, one is a vector. You cannot simply put a dot product or a cross product between these two. This is invalid. Okay, so this kind of operation is invalid. But suppose I have two vectors, like one is, let's say, A vector, let's say another one is B vector. You cannot simply write A vector, B vector like this. The normal multiplication you cannot write between two vectors. You cannot have a normal multiplication like this between two vectors. So when one vector is multiplied with another vector, the multiplication has to be either a dot product or a cross product, always. Okay, so never forget to put a dot or cross product wherever it is relevant. But when you multiply a scalar with a vector, A being a scalar quantity, you can simply write A into B, or you can simply write A into A vector if A is a scalar. So between as two scalars or between a scalar and a vector, the concept of this dot and cross product is not valid. So this is something very simple, probably you know, but often your seniors and other students, they do make a mistake. So this dot operation and the cross operation, they are the operation between two vectors only. And we call this dot product a scalar product, like I discussed before. Why do we call it a scalar product? Because the resultant of this dot product becomes scalar. Okay, the resultant of these two the two vectors operated with this dot product becomes a scalar. When you have a cross product, the resultant of this becomes it is still a vector. The resultant of the two vectors, like when you have a cross product, the result is still a vector. So that's why the cross product is also known as a vector product. Now let's get back to divergence. So divergence is when you have a del operator dot with another vector function. So this is your del operator space derivative del upon del z. So this is del z, okay, del upon del x, del upon del y. And when this vector operator del operator operates on another vector function, a vector function using this dot product, there is a dot sign here, if you can see that. So the result or the operation is called divergence of the vector field A. Divergence of the vector field A. Now, for example, this is one very simple example. Here, let's say you take a vector field like this. Vector A is equal to, there's a vector sign, sorry. Vector A is equal to xi plus yj. Now, let us calculate the divergence, or let us see how the vector will look like. Let me draw it, if I can draw it nicely or not. Let's see. So this is a vector on the xy plane. This is the x, this is the y. So at x equal to 0, y equal to 0, the vector magnitude will be, magnitude of the vector at x equal to 0 and y equal to 0 will be 0i plus 0j. It will be 0. So at this point, the vector does not have any amplitude. Now, at x equal to 1 and y equal to, at x equal to 1 and y equal to 1, the vector A now becomes 1i, 1j, 1j. If you take the magnitude of this, then this would be square root of 1 square plus 1 square. This would be square root of 2. It has a magnitude of 2. Now, let's get to another point called 1, 2. Then at this point, your vector A will become 1i plus 2j. And if you take the magnitude of this, it will become square root of 1 square plus 2 square is 4, square root of 5. Or if you go further into what is called another point 2, 2, there your vector will be 2i plus 2j, and the magnitude of this vector will be square root of 2 square is 4, 2 square is 4, square root of 8, like that. So as you move away from this origin, the amplitude of this vector will increase. So that means this vector quantity will vary with space. At this point, the vector will have certain magnitude, zero magnitude. As you move away from this point, the vector will have a certain magnitude. What is this point, for example? Let's say this particular point is 1, 0, x is 0, x is 1, y is 0. Then at this point, your vector will be 1i, j is 0. So magnitude of this vector will be I. Magnitude of this vector will be 1. All right. And if you go from this point to this point, this is, let's say, 2. This is 1. At this point, your vector will be, a vector will be 2i, 0j. So magnitude of a vector will be 2 square is 4 and square root. So this is 2. Magnitude of the vector is 2. All right. So what I'm trying to convince you here is that as you move away from the origin here, the vector magnitude will increase, and here along this at this point the direction is only along the I direction. See, j component is 0. There is only a direction along the I component. So along this direction there will be a vector along this only. Just a minute. Oh, hello, Henry. Class kala. Hola, hola. So, so if you plot this particular vector here, you will have a vector something like this. Let's say this is at this point the magnitude is only this much, and at this point the magnitude will be increasing. At this point the magnitude is increasing, and similarly along this direction also, you will find that the magnitude is increasing like this. So this is the kind of vector you would have using this mathematical representation. If you plot this vector, this is what you will be having. As you move away from the origin, the length of the vector or the magnitude of the vector increases. The length of the vector or the magnitude of the vector increases like this. So I hope you agree with me when I say that the length of the vector increases. You just put what will be the x value, what will be the y value at any particular point in space, then you will get this kind of vector. The direction also will change with the value of x and the value of y. Right. So as you see, this is a vector which is originating from this point, but near this point the amplitude is very less. So what I mean to say here is that this vector function is representing a vector which is diverging or diverging away from this origin. This vector function represents a vector which is coming out or spreading out from the origin here. Spreading out from the origin here. Okay. Now, if you have such vector, and when you take the divergence of that such vector, there is a del product here, del operator operating on this del dot vector A. Your vector A is this. So when you operate on that, I dot I will be 1, I dot j is 0, j dot I is 0, j dot j is 1, and k dot I is 0, k dot j is 0. You already know that. This is what I was repeating. Like this, right? So you already know this. So if you follow this dot product and the cross product there, you will find that eventually I dot I is 1, I dot j is 0, j dot I is 0, j dot j is 1, k dot I is 0, k dot j is 0. Then finally what we have is del x upon del x, del y upon del y. Then when you add del x upon del x is 1, this is 1, and then you get 2. That means this vector function has a finite divergence. The divergence of this vector function A is not 0. Divergence of this vector function is not 0. That means this vector has a divergence. Okay, this vector has a divergence. Now, if you consider this vector now, vector A is equal to 1j cap. So the vector direction is fixed along the j cap direction only. J cap direction is only along the y-axis. J cap direction is only along the y-axis, and the magnitude is also fixed. The magnitude is 1. So at any point, the magnitude, what is the length? The magnitude means the length of this vector. You take any point here, the length of the vector is constant. You see, the length of the vector is constant at any point in the space. The magnitude is constant, or the length of the vector is constant at any point in the space. And the direction is along j cap. J cap direction means it is pointing along the y-axis. Pointing along the y-axis. All of them are pointing along the y-axis, as you see in the picture here. All the vector represented by this thing is pointing along the y-axis, and they all have a magnitude of 1. Same fixed length. Now, now let us take the divergence of that vector again. Like this, divergence of this del operator operating on this 1j. Then what you have is I dot j is 0, j dot j is what? Del of 1 upon del of 1 upon y, actually. Del y, there's a typing mistake here. Del of 1 upon del y will be 0 because 1 is constant. K dot j is 0. So as you see here in this case, when you have a constant vector, like all the vectors are having a fixed magnitude of 1, and they all point along the same direction, the divergence is 0. That means divergence of 0 means, let us try to interpret what the divergence means. Okay. Now this is what I would like to conclude from there. Physical meaning of divergence. Physical meaning, what divergence of a vector really means. Say, in mathematics, we will be studying certain mathematical formulation like differentiation, integration. I have already talked about the meaning of differentiation. I have already talked about the gradient meaning. So what we need to know is what this kind of mathematical operation actually means. What does it refer to, and what does it interpret? What can we interpret out of that? So this is what we can deduce from the previous two examples. Physical meaning of divergence. Divergence of a vector field in any region of space is a measure of the net outflow of that vector field from the region of space under consideration. If in any region of space the number of vector field entering and outgoing are equal, then the divergence is zero there. That's exactly what I'm trying to conclude from here. Now, as you can see here, let's say you consider any region of space like this. This is, let's say, our particular region of space. This is our region of space enclosed by this closed surface. Now, you see that the vector field entering this 1, 2, 3 are entering. 1, 2, 3 are entering. That means 6 vector fields are entering. Now, if you look at this 1, 2, 3, 4, 5, 6, 6 vectors are leaving. That means the amount of vector field entering the region of space is equal to the amount of vector field leaving the region of space. So you can see that exactly the same amount of vector field are entering and leaving. That means there is no net outflow or inflow of the vector field. There is no net outflow or inflow of the vector field. Therefore, the divergence of this vector is zero. Now, going back to this example, now let us consider this region of space here. Let's say you have a region of space enclosed by a certain closed surface. See, vector fields are leaving 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of them are leaving. How many are entering this region of space? None, isn't it? So that means this vector field, which are represented by this mathematical formula, a vector is equal to xi plus yj, has non-zero divergence. Non-zero divergence means there is actually net outflow of the vector field. There is actually a net outflow of the vector field. All right. So when we have a net outflow of the vector field, then in that case, the divergence is non-zero. Now going back to this particular page, so you can see an example of an electric field due to a point charge here. This is an electric field due to a point charge. You consider any region of space or a closed surface like this, then you see that there is a net outflow of the electric field lines. There is a net outflow of the electric field lines. So here, if you have an isolated positive charge, there is no vector field entering the region of space under consideration here. However, there are electric field lines diverging or flowing out from this region of space. So if they flow out from this region of space, means the divergence of the electric field is non-zero, right? The divergence of electric field is non-zero. Or in fact, this is what the Gauss divergence, Gauss law is telling us. Probably you know this Gauss's law already. Gauss law tells us that divergence of the vector field is non-zero. It is equal to charge density within this region of space upon permittivity of the medium. This is what Gauss law was telling us, right? Now, let us consider this magnetic field. You know that magnetic poles, they always exist in pair, like North Pole and South Pole, and magnetic lines of force originate from the North Pole like this, I showed here in the, like it is shown here in this picture. Magnetic, here you see that one magnetic vector field is leaving this region of space, and corresponding to that, another magnetic vector field is entering. So these are magnetic lines of force. If you want to know the magnetic field at any point here, you just draw a tangent to the lines of force that will represent the magnetic field at that point. So a tangent to this lines of force means this is the magnetic field at this point. Okay. So when you consider a magnetic field lines like this, for any vector field leaving this region of space, you will have another corresponding vector field entering the region of space. Because as long as there is a north pole and south pole, magnetic field lines originate at north pole and terminates the south pole. So this concept will let us know that divergence of B is 0. There is no net outflow of the vector field. Or you consider this region of space also, you see that number of vector field entering the region of space is 3 here, and number of vector field leaving the region of space is 3 again. So that means there is no net outflow or inflow of magnetic field vector from this region, because number of lines and vector field entering and number of vector field leaving, they are exactly equal. All right. So see, this divergence of B concept occurs only due to this like presence of two magnetic poles. See, suppose I can have a single magnetic pole like north pole here. Just in the case of a positive charge here, you will find the magnetic lines of force will leave from that north pole, and you would not have any magnetic field lines entering the north pole, isn't it? So if we can have a magnetic monopole like that, then the divergence of the magnetic field will be non-zero. But in reality, we can never have a magnetic monopole. Even if you feel that, suppose I break the magnet here, even if you break the magnet here, one side will still be north pole and another side will still be south pole, and you will still have magnetic lines of force leaving and entering the south pole. So magnetic poles, as they always exist in pair, and we do not have a magnetic monopole, there you will have the divergence of B as 0 always, right? Now, so I thought I would cover a lot of topic. Now it's already 12. So I have some other work, but anyway, let us try to continue at least the concept of curl here. So curl of a vector field is when you have a cross product operation between del operator and the vector function. So when you have a cross product operation between a del operator and a vector field, then that operation, that mathematical or vector operation is called curl of a vector field. So when you have a del operator, means it's a kind of a cross product between two vectors. You know that, like this is, suppose this is like this. You have two vectors, del upon del x. One is of course the operator, del upon del y, j, plus del upon del z, k cap, cross product between this. That means a1i plus a2j plus a3k. So when you have this kind of cross product between two vectors, you know that you can write the cross product like this: I, j, k. This you already know, I hope, in class 12. And del upon del x, you can express it like this, right? So when you express it like this, you take a determinant. So I del of a3 upon del y minus del of a2 upon del z, and similarly j will be del of a1 upon del z minus del of a3 upon del x. Like this, you can write curl of A. Now, suppose I have a vector field like this. A vector is equal to minus of y I plus xj. And like I explained before, if you represent it graphically on the xy plane, this A vector will be something like this. Okay, A vector will be something like this. Now, you take a cross product between the operator and this vector A. As I said, this is the curl. So this will be you just take a cross product. This is what you get. Finally, if you follow the mathematical steps here, curl of vector A will be 2 times k vector. That means curl of vector A is non-zero. Curl of vector A is non-zero in this case when you have a vector field rotating around like this. This mathematical expression, if you plot it, this is what you get. Okay, so when you have a vector field rotating around the origin like this, you take a curl of that vector field, this is non-zero. Now suppose you take the same vector xi plus yj. What is xi plus yj? Xi plus yj is here. Xi plus yj is this vector field that I already draw here. So if you take the curl of this vector, now curl is again this operation, you already know. In determinant form you can write the cross product between del and a vector, and if you take the determinant, then this is what you get. And finally what you have is that curl of a is 0. Curl of a is 0. Okay, so here in this rotating vector field, curl of a is non-zero. Here in this non-rotating or diverging vector field, this vector field is spreading away from this particular origin point. There is no rotation. As you see that rotation means a vector has to rotate around. Here you see that all the vector fields are straight lines pointing away from this origin. So when you have a not rotating vector field, curl of A is 0. When you have a rotating vector field, curl of A is non-zero. Then what is the physical meaning of curl of A? So you see that curl of A, curl of vector field, please mute yourself. Curl of a vector field, as you see, it's a measure of the rotation of the vector field. Okay. In static charge distribution, like like shown here, like the one I shown here, in static charge distribution like this, the electric field lines are straight line and they are spreading away in every direction from a positive point charge, and they are converging to a negative point charge. You already know that. The electric lines of force indicating the electric field vector direction does not change their direction. Therefore, in static charge distribution, curl of E is 0. Because in static charge distribution, if it is a positive charge, electric field lines are spreading away from it. It's a straight line and pointing away from it. If you have a negative charge, it's another straight line converging towards that negative charge. So there is no rotation of the electric field lines here if you have a static charge distribution. When you don't have any rotation of the electric field lines, your curl of E is 0. That means curl of E measures rotation of the vector field in which it operates. Okay. Now, however, like later on you will study Faraday's law, you will find that curl of E is non-zero there. But in Faraday's law, curl of E is non-zero because the electric charges are not static. They are not electrostatic situation. They are electrodynamics. The electrons are moving around. So when the electrons are moving around, curl of E will be non-zero. And you know that Faraday's law is, probably some of you already know, I think you have studied this. Curl of E is minus of del B upon del T. So when we have a motion of charges, then curl of E is non-zero. That is del minus of del B upon del T. But when you have a static charge distribution, the electric field lines are always straight lines. They do not rotate. There you will have curl of E as 0. And on the other hand, as I discussed, the magnetic field lines, the magnetic poles, they always exist in pairs, and the magnetic field lines originate from North Pole and terminate at South Pole. That means in order to do that, the magnetic field lines will, instead of a straight line, the magnetic field lines are actually rotating lines. The magnetic field lines are not a straight line, they are rotating around like this. So because of this rotation, you'll see that curl of B is non-zero. Curl of B is non-zero, and some of you probably know already what is the curl of B. Curl of B will be defined by your Ampere's circuital law, which says that curl of B is mu J, where mu is the permeability of free space. So curl of B is non-zero, it equals mu J. So that is what we can cover in one lecture. Divergence means it's a measure of the net outflow or inflow of the vector field. Curl of a vector means it's a measure of the rotation of the vector field. If the vector field is non-rotating, the curl is 0. If the vector field is rotating, curl of the vector field is non-zero, like the magnetic field shown here. Okay, so I think I will stop here. These are some of the examples I thought you would work out because you already have the materials with you. So please enter your attendance in the chat box by typing your roll number in full, and then after that exit the meeting. Once if you type once, do not repeat please, because it's already there. Okay, yeah, thank you everyone for attending the class. You can exit the meeting now.
Thank you, sir.
Sir.
Sir, will you share the record, the screen record, sir?
Yes, I will record. I will share the video record again. Okay,
Thank you, sir.
exit the meeting.